Professor Anupam Mazumdar here, and he will talk about quantum gravity via entanglement of masses. So, a new approach to understand some aspects of quantum gravity. So, Professor Mazumdar, please start. And for
Thanks. Thank you very
questions,
much.
I mean, you can take it at the end of the lecture or in between. I mean, it depends on your choice. So,
I can take any time, so don't hesitate. You just
oh,
raise your. I mean, you can just ask me the question anytime, and I'll be happy to take it. Okay, so
yeah, please.
thanks. Thank you very much for your kind introduction. It's really my pleasure, great pleasure to discuss something which I'm quite excited about it now. And the reason I'm excited, perhaps, I hope I will be able to share with you, and I hope that something, can be done with our colleagues from India in this direction in near future. And so let me first introduce my colleagues with whom I have really started this work. So actually, I'm not an expert in many of the things which I'm going to talk today, but in the process, I have learned quite a lot of these things, and partly because of my very close friend, Sogato Bose. He and Bose and I myself, we have studied together in IIT Kharagpur, did our undergrad, and then we came to the same school, Imperial College, to do our PhD. So I have known him for almost over 25 years, and he taught me something, and because he's the master of quantum optics and quantum information, and I came from the gravity side, and rest of our colleagues are purely experimentalists. They are experimentalists in various directions, quantum information, quantum technologies, quantum computing, and things like that. So that's the first paper which we wrote way back in 2017. And then we have written a couple more papers discussing some of the technology aspects. And you would realize soon that part of my talk will be purely theory, and part of my talk will be talking about a little bit of technology. So today I'm going to talk about quantum gravity witness via entanglement of masses. So we call it a QGEM protocol. And way back in 2017, there was another group from Oxford who wrote the paper, but severely lacked the technological aspects. They just had the concept, but what matters here is the technology here. And hopefully I will raise some of these issues now. Okay, so the question is very, very simple. Is gravity classical or quantum? Indeed, a very simple question, but it's very, very hard to answer. It has all, we know that gravity has been extremely, extremely successful. There's no doubt about it. Quantum mechanics has been extremely successful. Individually, these two topics are very, very successful. But whenever we try to marry them together, there are many issues and there are many problems, and we don't know how to solve many of those problems. But so it turns out that even doing the experiment becomes very hard. And if I'm looking for gravity's Cheshire cat, it depends very much, because we know that in a classical gravity, we have a very interesting concept which appears, which is the Schwarzschild radius, even for a static system. Now, the beauty of a cat, or the ugliness of a cat, let's put it this way, depends very much on its size, the macroscopic size. If I'm looking for the real beauty, the cuteness of a cat, which is a quantum aspect, then I really have to approach to the Schwarzschild limit. And it becomes extremely hard to do this kind of experiment. How could I come very, very close to the Schwarzschild radius to see some of its quantum beauty? So in some sense, it poses a problem even at the level of experiment, that how do I really see the cat's, the quantum aspects of this big cat? So there are various levels of excitement. You can say that, you can ask many questions. After all, this gravity has been more than 100 years with us now. Quantum mechanics has equally been for long enough time. So now you can ask various kinds of questions. And, theorists are very, very, I guess, excited by many interesting aspects. And you can ask, can I really take a simple graviton and put in a quantum superposition in a lab? Like what we have done in the case of photons. But unfortunately, it's impossible. It's very hard because of, one thing you realize that gravity is very, very weakly coupled, theory. So that makes it very hard. Now, you can ask a very another stupid question, perhaps, that you take two atoms and talk about exactly the coalescing of atoms, like in the case of coalescing of black holes, which LIGO, Virgo, and these detectors have seen. Can you see the loss of gravitons in the process? And again, the answer is perhaps extremely hard, because you can do this calculation in the back of your envelope, and you see that the number of gravitons which you would lose is so few that it's hardly detecting them would be extremely hard problem. Now, the third and last, perhaps the simplest and the lamest approach which you can think about, and ask the question: can you witness quantum entanglement due to quantum nature of a graviton? And we believe that perhaps this is doable. This is the experiment which one can do it. So the question is, if we can do such an experiment, what should be the right protocol to ask? What should be the kind of question which John Bell asked many years ago, way back in the 60s, that how do you know whether quantum mechanics is really quantum mechanics? It's not because of some hidden variable, or there are some other issues like that. So this is the kind of razor-sharp question which we wish to ask. And I have had many lively discussions with, of course, my collaborator Bose, then Ambion, Oshtaker, Aspel Myers is an experimentalist, Valery Frolov, Horowitz, Myers, Don Page, who has pioneered himself. His work had been the pioneering work which he started in the way back in the 80s. And then Penrose, Rovelli, Ashok, and Veneziano, Bob Wald, and many other people have got interested in this topic recently. And so I hope that I will be able to share some of my thoughts with you today, and would be able to convince some young people to take this opportunity, because even I'm quite old. In 30, 40 years, if this experiment can be done, even who knows, I may not be here. But anyway, coming back to the question, so we are looking for quantum gravity witness. We want to see the witness protocol for quantum gravity. The question is, how do I read the witness? How do I know whether it's really quantum, and what are the associated challenges, and what's the future program? And then I will deduce or I will talk about some aspects of purely theory motivated from the experiment. Usually in quantum gravity, what has happened is that you are motivated by beauty of the topic. Pure sheer mathematical beauty drives you towards quantum gravity. But now perhaps with the experiment you can say that, look, maybe the experiment should guide the theory. So that's the kind of approach we are taking. Okay, so just a brief recap about gravity, just to put everyone on the same page. It is universal, it is extremely successful. With the LIGO, we have seen the success of general relativity, there's no doubt about it. It has a very simple universal coupling with the matter. The matter is T mu nu, and H mu nu is my graviton. But of course, it being a very beautiful theory, it has also some drawbacks. The classical general relativity has singularities which are very hard to tame. In various approaches, you try to tame it in different ways, but still there is no consensus that how do you resolve the cosmological singularity, for instance, how do you resolve the black hole singularity. Who knows, maybe even the local field theory which we are talking about may not be sufficient. Maybe we have to go to string theory, or maybe loop quantum gravity. So the verdict is still open, but my intention today is not to get into these topics, but rather to bring your attention to this very simple plot, which is fairly old by now, which was done in 2007. And trust me, almost 13 years have gone by, but the progress has been very little. So this is the plot. You see that on your y-axis there's alpha, and the x-axis is lambda. The experimentalists like to probe the nature of gravity, purely classical gravity, essentially looking at the 1 over r potential. So you have a correction, 1 over r, the Newton's potential, plus Yukawa kind of potential, and alpha and lambda are the two parameters. So as I said, that it's fairly old plot, but the yellow region has been excluded by various experiments, and the white region is the one which is allowed. And if you look carefully, you find that very small values of alpha. So essentially, I'm talking about just pure 1 over r correction is least understood, least constrained, classically even. We don't know how even 1 over r law of Newton's gravity behaves at very short distances, below millimeter distances. We have no experimental proof. And you see that how much extrapolation we make. And if you convert this scale into some energy scale, that corresponds to roughly, if I take 10 raised to minus 5 meters, that would correspond to something like 10 raised to minus 2 electron volt to the power 4. If I take that roughly just the length scale and convert that into energy. and you know that the dark energy is roughly 10 raised to minus 3 electron volt to the power 4, and you see from 10 raised to minus 2 electron volt to the power 4, all the way up to 10 raised to 27 electron volt to the power 4, which simply do not understand even classical gravity, whether gravity is attractive or repulsive or how it behaves. And not only that, on top of that, we try to formulate quantum theory of gravity. So it's not to criticize why we formulate quantum theory of gravity, but it's to highlight the problem that when I want to understand the weak nature of the pure interaction, sheer interaction of gravity, is extremely, extremely hard because of the weakness of gravitational interaction. So who knows, new effects of gravity could be all around the corner. Now, having said so, I mean, many people have thought about bringing quantum mechanics and gravity in a laboratory. We are not the first people. So way back in 70s and 80s, there was a famous experiment due to Colella, Overhauser, and Werner experiment. So the Colella's experiment was performed in the gravitational potential of Earth. Now you see, and they have measured the phase. The phase due to Earth's gravitational potential. Now you wonder that, wow, I mean, gravity is so weak, how it is still even detectable. And the reason it's detectable because what enters into the phase is your Newton's constant. Of course, the masses of your object in Cow's experiment was the neutron, and divided by h bar. So G is extremely tiny number. H bar is extremely tiny number. But the ratio of these two may not be tiny. So there may be a sweet spot. If you can tap that sweet spot, you can see certain effects due to pure gravity. And that's what Cow did in the experiment. And there are now various proposals. Way back in 2000 in Grenoble, people took the cold neutron, and they bounced the cold neutron and measured the energy states of these cold neutron. So many labs can do these kind of very sensitive experiments. So the idea here is essentially what you're trying to do is that you're fixing a box and you're trying to, a simple quantum mechanics you're trying to do. You're taking a, say, ping pong ball and you're trying to quantize the energy state of this ping pong ball in the fixed gravitational potential. Excuse
me, Anupam. So this experiment, is it regarding the measurement of the arm of Allen phase?
Is due to unequal path lengths. So in the Cow experiment, the two path lengths were slightly different. And as a consequence, even though you close the loop, you see that there is a residual classical phase. And that's what Colella, Overhauser, and Werner measured way back in late 70s.
So it's not a geometrical phase. Or, is it an ordinary interference path distance multiplied by 2 pi by lambda naught phase or what? That's what I would like to know. What kind of a phase are you talking about here? Or is it a geometrical phase in the sense of arm of Allen?
Unfortunately, they did not measure the geometrical phase. It's not a geometrical phase, but people do measure geometrical phase. People measure now this famous mathematician, Indian mathematician, I'm forgetting his name, he was in Princeton. Anyway, I recall his name. And so people have measured these kind of phases in the laboratory, but not the gravitational one. So the gravitational one is purely essentially the classical phase. It's not a geometrical or topological in nature. Okay, so maybe we can discuss it after the talk. Maybe we can have more discussion in this regard. So one of the things which I want to bring your attention to a very interesting paper by Don Page and his collaborator Gilker. So before even we thought about this kind of experiment, people have been thinking about how to prove whether gravity is classical or quantum. And to my knowledge, this one paper comes very close to what we are talking today, except that it could not ascertain whether gravity has to be quantum. So the idea was that they were approaching the problem in a semi-classical regime, where they took the energy momentum tensor to be quantum. So essentially, you take hydrogen atom, which is quantum, but treating gravity is like classical. And the idea was that statistically ascertain whether you required quantum gravity or not. And as you can see from just from the abstract, they mentioned that yes, they have sufficient proof for against semi-classical gravity, but it does not necessitate that gravity ought to be quantum. So the idea is very simple, that if your particle is in macroscopic superposition, then either the particle would be here or in some different place. And then you can measure the gravitational potential and statistically try to rule it out, whatever is the outcome. So Page and Gilchrist's paper came fairly close to ruling out or saying that semi-classical nature of gravity should not, is not supported by the experiment, but they could not conclusively say whether the gravity ought to be quantum or not, or whether the gravitational field ought to be quantized or not. So there was another experiment which became very, very popular. People came to know immediately this bicep experiment, which every one of you perhaps have come across. And people thought initially that they have seen the primordial gravitational waves, and that if you would have seen it, it would have been remarkable. But unfortunately, it was a false alarm. They didn't see the primordial gravitational waves. They did see the polarization effect, but not due to primordial gravity, but due to dust. But then immediately there was a paper, a couple of groups have written the paper. One prominent paper came by Krauss and Wilczek, and they pointed out immediately that, look, in this calculation, if you assume the quantum initial conditions, then you get h bar. And then that shows that gravity ought to be quantum if you ever see quantum primordial gravitational waves. But people before that even knew that this kind of two-point correlation function can, yes, you can put quantum initial condition, Bunch-Davies vacuum or some other vacuum, and proceed the calculation. But you can mimic this h bar effect even by a classical initial condition. So h bar is just showing that somewhere h bar appears in your calculation does not suffice that your theory is quantum. And just by saying that h bar is there, you are not testing whether gravity is quantum. You are merely testing essentially certain algebra, in terms of mathematical algebra. You're testing that. So you can mimic this number. After all, h bar is a number, and that you can mimic by choosing maybe very ugly initial conditions whatsoever. But nevertheless, that's not suffice enough to say whether gravity is classical or quantum yet. So having had this brief discussion, so we are looking for something very razor sharp kind of argument, some kind of witness. And if I say that, hey, look, if the witness is positive, then the gravity ought to be quantum. And if the witness is negative, we cannot say anything, or we have inconclusive result. So this is the kind of protocol or razor-sharp argument we are trying to think about here. And this is all about this quantum gravity-induced entanglement with masses protocol tells us. So what are the key ingredients? So before we discuss what key ingredients we need, we have to decipher between quantum mechanics and classical mechanics, and we have to pick up the concepts in quantum mechanics which cannot be mimicked in a classical world whatsoever. And the two important ingredients which comes to anyone's mind, one is your the entire concept of Schrödinger's cat, that quantum superposition of localized objects, whether the cat is dead and alive simultaneously, that cannot be mimicked in any way in a classical world. So if you can create a macroscopic quantum superposition of localized masses, since mass corresponds to your curvature, very tiny curvature maybe, but nevertheless, you can put even curvature in a superposition. So that's something, this feature is something very essential to any experiment if I want to test it in a laboratory as far as the gravity is concerned. The other key concept comes in is the quantum entanglement. Again, it's purely a quantum concept. It has no classical counterpart whatsoever. And the best example is that you can, from a vacuum, you can create electron-positron pair, and that this pair is always entangled. You cannot talk about the wave function of electron and wave function of a positron separately. When you always talk about the electron-positron wave function, and that tells us immediately the vacuum is a highly entangled system. And so again, this entanglement is another non-classical feature which is essential for any experiment in quantum gravity. So these are the two key ingredients which we need. Sorry, can I interrupt you for a second? Yeah, the question.
Yeah, so I was asking about this quantum superposition. You see, ordinary quantum mechanics is a linear theory. The Schrodinger equation is linear. But there's no guarantee that if you do have a full quantum theory of gravity, that it's going to be linear. And superposition of states are going to occur. So just the requirement that you have superposition is not enough to preclude gravity, right? Because it could be that you have non-linearities which does not allow you superposition.
But you see that where the nonlinearity appears, in gravity, nonlinearity appears in your space-time, but in Hilbert space, it can still be linear. So it depends very much how you perceive nonlinearity and where the nonlinearity should appear. Now, you're absolutely correct. If you want to modify your Hilbert space by nonlinear algebra, yes, you can try to do that. But people have seen, first of all, the macroscopic superposition in a laboratory with masses. And now if I take it very simply, that mass has gives rise to a certain amount of curvature. So even if there is a certain amount of nonlinearity which will creep in because of a nonlinear gravitational interaction, but I can still imagine that my gravity at the lowest order, should exhibit some kind of like a linear superposition. So, as you will see, that the kind of experiment which we'll do it not with very, very heavy system. There will be mesoscopic system. So they are very, very light in general, but has certain amount of gravitational interaction. Okay, well, this is the kind of picture. It's a kind of like a picture which has already been there in Feynman's book, I think. He was the first one to actually think about these kind of problems even before many of us. So essentially, can you create a superposition? Can you bring in the superposition principle? So underpinning the superposition principle in quantum mechanics has been there, and people have seen, for instance, in Vienna, people have taken 10 raised to minus 23 kilogram graphene, fullerene essentially, and the fullerene balls, and they have tried to put, they created macroscopic superposition, which they could maintain for a couple of seconds, essentially, milliseconds, I think, up to nanometer distance separation. So they have been successful in creating this kind of superposition in a laboratory. And one other thing which is very important is that the optionalness of, that any experiment which people do in a laboratory requires certain amount of optionalness. And you would realize that off-shell picture, sometimes you call it a virtual excitations or off-shell excitation. This is again inherently quantum in nature or non-classical in nature. So whenever you talk about beam splitter essentially gives rise to certain amount of optionalness. Whether I do a diffraction or I do a beam splitter, it's kind of like a tunneling process. And tunneling process essentially is a non-classical phenomenon. So anyway, so now the question remains is that how am I going to test whether gravity is still quantum? So as I said that in the case of photon, we know, QED, we know it has been a huge success by itself, and photon, in the case of QED, we know that photon is quantum, there is no doubt about it, but it took, but creating the superposition for photon, it took a long time. Way back in 80s, people realized that you can put superposition of photon in different wavelengths, different frequencies, different polarization, and now it has become a routine test in many of the laboratories. So this is a picture from the Max Planck Institute for Quantum Optics, the Gerhard Rempe's group, where they have tried to put superposition of photon. So one of the theorem which plays a very crucial role, and this is the place where actually the cross-fertilization between two different fields have become very, very successful in this respect. And I was not aware of this theorem at all. And I was told by my colleague, by my collaborator, Sogato Bose, and the theorem stands as a local operation and classical communication. It's called LOCC. So what the theorem states is that suppose you have got Alice and you have got Bob. Imagine that Alice has a quantum system, Bob has a quantum system, and they are interacting through a classical channel. And if it is so, if they are interacting via a classical channel, so the theorem says that Alice and Bob cannot entangle with each other. So one very simple example will be that suppose if I give you a coin has a Hilbert space, and I assume that my coin is quantum, so I have heads and tails, and I have a coin which Hilbert space spans 2 up and down, and suppose you toss the coin billion times, I toss the coin billion times at my end, and suppose we are interacting through classical interaction or classical channel, then we will not be able to influence each other's outcome. So I will not be able to influence your outcome. It will be 50-50 always, 50% heads, 50% tails, and similarly, my outcome will be 50-50. You will not be able to influence my outcome. But now if you can reverse this argument, if you say that somehow can you create LOQC, what it means is the local operation and quantum communication, then essentially you can show that you can establish an entanglement. I will be able to influence your outcome as a consequence, and you would be able to influence my outcome. So as a consequence, the witness will not be 50-50, but it may be 51-49, or maybe 51 point something and 49-48 point something. So that's the demarcation which one can actually bring in with the help of this LOCC. And in LOCC, LO stands for the local operation. And what local operation means is that your unitary evolution, or where you have conserved energy momentum tensor. So these are all local operators, essentially. So, and this LOCC theorem was proved by Bennett, who is the father figure of quantum computer, way back in 1996. And in the beginning, they proved this theorem with the help of majorization and many other mathematical techniques. And now it has been quite a routine subject in the quantum information. And this is the part when I came to know, I immediately reacted to this LOCC theorem and say that, look, if you can do LOCC and if you can establish it, then perhaps you can also try to violate it by saying that instead of classical communication, you have a quantum communication. So now coming back to gravity, or as a matter of fact, even any 1 over r potential, it doesn't hold for gravity, it holds for even any 1 over r potential, even in the case of photon as well. Now, if there is a very hardcore classical mechanics person, if someone does not believe in, say, quantum mechanics, would say that, look, I mean, after all, the 1 over r potential which I observe can be mimicked can be obtained essentially classical action at a distance, and that has been there since the days of Newton. So this is purely a classical picture. So but you know immediately that it will violate your special relativity. It's the same butterfly effect in Tahiti. If in Tahiti there's a butterfly flies, I should be able to feel this effect instantly at my end. And so this is the problem with the classical action at a distance. But then you can ask the question that even the potential V over R potential, so V of R potential, the potential which is 1 over R, which you obtain, what is its origin? Can it have a classical as origin as well as quantum origin? And as I said, that yes, classical origin is very much there since the days of Newton, action at a distance, essentially. And in quantum mechanics or in quantum field theory also, you can derive a potential. So essentially TFI is just nothing but the transition matrix from going from initial state to final state. And the first term in my perturbation theory, so this is the kind of quantum mechanics we teach to our undergrad student, Griffiths level quantum mechanics, nothing very fancy, that in the very first term which you appeared, we're going from initial state to final state in presence of a potential. This is purely a classical effect. So this was performed way back in days of Chadwick when he took the alpha particle and bombarded the gold foil to understand the nucleus, the potential of the nucleus, essentially. So that's the kind of effect which even when you do the series expansion in the transition matrix, you get from the first term. But the second term in the transition matrix is nothing but the second order perturbation theory in quantum mechanics. Essentially, you see that you have a state, intermediate state J, and you're summing over all this intermediate state. And this one is actually inherently a quantum object in the sense because there is a mediator. A mediator can absorb your energy momentum tensor and can transfer that in different two space-time points. Now, having said this, there are many people like the very famous physicist Belaku. He was actually supervisor of Salman. I've forgotten Salim. He was in Los Alamos. He was a supervisor of this person. And anyway, but he still believes that the scattering diagram at the tree level is not quantum. He believes that it's still classical. But there are very hardcore people, even in quantum field theory and quantum gravity, have different opinion about it. So anyway, coming back to this diagram, the second diagram which I was mentioning, this the transition matrix, you see that if you sum them up, so there are two possible time order diagrams you can construct. When you sum them up, you get your Feynman propagator. And if you recall in the Feynman propagator, your vertices they conserve the energy momentum tensor. So they're essentially the Noether's currents hold in the vertices, but in the propagator is the off-shell or a virtual or particle, which we call it many times. But keep in mind that this virtual particle does not satisfy your classical equations of motion. So this is the demarcation. If you say that, look, I want to see some non-classical feature in my scattering diagram, so this is the part which you can essentially try to pick up, and you can try to exploit that. So here comes the local operation in quantum communication. So as I said, suppose I take two massive particles. At the two ends, I have a unitary operation at point particle A and point particle B. And if I have an off-shell exchange of a graviton, so I have a local interaction at both the vertices, and I know the graviton off-shell propagator, and I derive the 1/r potential in the three-level exchange of a graviton, and from here I derive the 1/r potential. And as far as I'm doing the calculation around Minkowski space, I really don't have to worry from the point of view of gauge, fixing the gauge. There are many ways you can fix the gauge. It doesn't really depend, like in the case of time-dependent background, you really have to come up with a problem with fixing the gauge. But here in the Minkowski space, these problems are not there as such. Now, what are the three discriminators essentially? I will go through all the three diagrams. So the first one, as I said, that in a perturbation theory, is just nothing but your classical scattering in a given potential and going from initial state to final state. That's the first term in the perturbation theory. That will also give you, if I measure the phase, that will also give you G over H bar correction. The second term in the transition matrix, which I believe is a purely quantum because it's happening through off-shell exchange of a graviton. This will also give you the same phase G over H bar, but now there is a difference. The difference is that the two ends of your Alice and Bob, in this case, two particles essentially, they are getting entangled because of off-shell exchange of a graviton. Now, just for the sake of illustration, I have given you the third diagram. And the third diagram, you can imagine that suppose in 4 dimensions, so in 3+1 dimensions, you take cosmic strings, infinite cosmic strings, and you know that very well that if you take in 3+1 dimension a cosmic string, it does not give you any tree-level potential. It does not have any 1/r potential. And the reason is very simple, because the way you create a cosmic string in 3+1 dimension is you take a sheet of paper, 2-dimensional sheet of paper, you cut a deficit angle, you take the tip, and you blow that up. Since the 2-dimensional sheet does not have any curvature effects, so it does not generate any potential. So that's the reason if I take in 3+1 dimensions, infinite string, they will not have any gravitational potential between them. However, the gravitational potential does appear purely from one loop effect. And this calculation was performed by Mark Weiss and his student at that time. And it's a very beautiful paper. I would recommend any one of you to look into this paper. It's not very well cited. Mark Weiss is a highly cited physicist, but this is the least cited paper of Mark's, but very beautiful calculation. So sometimes citations shows that it's just the sheer trend, not the real physics comes in. Anyway, so there are 3 possible diagrams which you can talk about, 3-level diagram, even 1-loop effect. But the problem in the 1-loop effect comes in because if you want to measure the phase, that comes with this price. The price is G square over H bar over H bar. So effectively the phase is G square. And G being a very, very tiny number, measuring any of these effects will be impossible in the entire humanity, because the effect is so tiny that I can never ever build any experiment where I can see this very tiny number in a quantum phase. But as I said in the very beginning of my talk, that anything which is G over H bar, I can play with the rest of my parameters and can find a sweet spot where I can measure this phase. So that's the hope. That's the best hope we are left with in our laboratory. So what is the QGEM protocol? So the QGEM protocol is that now this part I'm going to be I'm going to spend a bit of time in the experimental side, because that's the one which is the future for us. So the idea is that, as I said, that you have got Alice and you have got Bob. Alice has got an interferometer, Bob has got an interferometer, and these are neutral particles. And for the timing, let's assume that there's no other interaction other than gravity. And it will turn out that it's not correct. There's always some interaction other than gravity. But let's assume that there's no other interaction other than gravity. The Alice's interferometer and Bob's interferometer, they're interacting only through gravity. Then what would happen is that, as I explained you with the tossing of the coin, if the gravity is quantum, then Alice's interferometer and Bob's interferometer will be entangled. And once I close the Stern-Gerlach loop, and then I can measure the spins. So I have embedded a spin in these objects. And for the time being, we are taking these objects to be diamonds because it has certain nice features. One of the features of diamond is that inside the diamond, there's purely a material science, essentially. What happens is that there's an NV center point, nitrogen valence bond, which is a free bond. And the experimentalists, what they can do is that they can take electron spin and they can embed that inside the diamond. And so as a consequence, although it's a neutral particle, neutral object, now it has got spin, which it can respond to an inhomogeneous magnetic field of your Stern-Gerlach experiment. So these are two Stern-Gerlach setups, and you're trying to close the loop by playing with the magnetic field, and then you are measuring the witness. The witness is by looking at the spin. How many times I'm getting a spin up and how many times I'm getting a spin down. And then I'm building a correlation. And if the correlation has a quantum feature, which is entanglement feature, I will be able to see it. And if I don't see anything, then I will not be able to conclude anything about the experiment. So that's the kind of protocol which we are talking about. And the entire system is a freely falling system of superposed masses. So one of the difficulties is that how do you create a macroscopic superposition? And it is extremely hard. So as I said, that right now we played with diamond, but even I know that in future I have to invent some completely new material. Diamond has many other problems. Even the kind of diamond which we are talking about, you need to polish the surface of a diamond so fine that it cannot be done. I mean, it has to be manufactured in a certain laboratory, and the best way of polishing the diamond is actually through the olive oil. In the diamonds which our ladies, in the jewelry, and the people like to use the jewelries, they polish it with this olive oil. But these diamonds are completely manufactured in laboratory. We cannot afford to have any surface impurity, because imagine if there is a surface bond which is left over, then it can even attract an electron and can destroy my superposition. It can decoher the system. So there are many challenges, but I think in spite of these challenges, it is fair to say that people have demonstrated it, or mathematically, or not experimentally yet, that 100 micron separation can be reached for roughly 1 second. You can create a superposition for a mass roughly around 10 to the minus 14, minus 15 kilogram system. So in spite of these difficulties, it is possible to create a macroscopic superposition. So again, as I said, I briefly explained it, that you allow the two system, you let it free fall, and then you bring this, make a complete one loop in the Stern-Gerlach, and then you measure the spin correlation function. And through the spin correlation function, you are going to certify whether the two systems, system 1 on your left-hand side and system 2 on your right-hand side, are getting entangled or not. So what happens to the entanglement phase? You can compute the entanglement phase between these two masses, M1 and M2. And this entanglement phase comes with the G over H bar effect. The masses of the system, the flight of, the entire time tau flight of operation, and the maximum phase arises by the closest separation, which is D minus delta X. So D is the center of mass, imagine, distance, and delta X is my superposition. Now in an experiment, of course, delta X will not be the same, but for theoretical calculation, just to give some idea, we take the delta X to be exactly the same, and then this is the phase you obtain. So the entanglement phase. You can put some numbers into that, and if you want this phase to be roughly order 1, then you know the G, you know the H bar, then it requires that what should be masses and what should be the tau. So there is a sweet spot, and the sweet spot tells me that if I take the mass to be roughly 10 raised to minus 14 kilograms, with the separation, the closest separation d minus delta x to be roughly 200 micron, and delta x is roughly around 100 micron, then I can obtain phase which is roughly order 1 phase. And the way the crucial aspect is to realize whether the entanglement is happening is by looking at the correlation. This is the spin-spin correlation, sigma x, sigma y, sigma z. These are the Pauli matrices. And so you build a basis-dependent correlation. And so when in 2017 we gave this basis dependent witness, but it turns out that now people have constructed many better witnesses, and I will show you one of the witness for my colleagues who have come up with a better witness to measure this entanglement phase. So again, as I said, that what is happening is that in spite of these very tiny numbers, what is appearing is G over H bar, and G is a small number, H bar is a small number, but still you have a sweet spot. Now, in order to do this experiment, let's go back to this picture. As I said, that you can isolate everything except gravity, but that's not completely true, because even if I get rid of all the electromagnetic charges, so I can make the system neutral, but I cannot get rid of is the Casimir-Polder effect. So Casimir-Polder effect is just because of the QED effect. It's the vacuum fluctuation in the photons. And trust me, the next street of my home is the Casimir Street, because I'm in Groningen in Netherlands, and Casimir is a well-known scientist from Netherlands. So his name is there everywhere. So I could not forget his effect. So in some sense, so in order to get these numbers, I have to make sure that the Casimir, even the Casimir, effect can entangle the masses. So I need to overcome that phase. So because it turns out that even if I neutralize everything, the Casimir-Polder potential acts like a biggest background in these ranges which we are talking about. So in 2017 paper, we had to make sure that in order to exceed this Casimir-Polder effect, which goes as 1 over r to the power 7. So if you take two spheres, the Casimir potential will go as 1 over r, the separation to the power 7 in a denominator times your dielectric properties of your material. And if you take the mass to be diamond, the matter to be diamond, you know the dielectric properties, you can compute everything, and you know how much is the phase. So we need to make sure that here the gravitational phase dominates at least 10 times that of the Casimir-Polder potential, or Casimir-Polder entanglement phase.
Sorry, another interruption, Anupam. This phase that you calculate, this is nothing to do with quantum gravity, right? It's just classical gravity in a sense. Because you're not looking at entanglement of gravitational quantum gravity states. You're looking at entanglement of quantum spin states, ordinary spin states, induced by gravity. But the gravity is classical, is it not?
As I said, you see that this is the experiment, this is the point which I was mentioning in this slide. So what I'm looking at, that there are two terms in your transition matrix. The first term indeed gives you a classical result. It's a classical scattering. But the second term requires your concept of a propagator. And propagator, here the Feynman propagator, is off shell, is a virtual. And for me, the virtual quantity is not a classical quantity. For me, it's a non-classical entity. It doesn't satisfy your classical equations of motion. So in this respect, even though it's a tree-level diagram, which I'm capturing, I'm actually following the LOQC. So the interaction between point A and point B is happening through a mediator, and this mediator is a off shell. You see that this is the connection I'm trying to build. Of course, I mean, we would like to do this kind of experiment with the two cosmic strings. But there you could see one loop effect. But this experiment is extremely, extremely hard to do, precisely because the phase which it will induce is very, very, very tiny. So what we are testing is really the perturbative quantum gravity. So this is the level at which we can do the experiment, not really the non-perturbative aspects yet. Anyway, so we can again discuss this topic again after my talk. So coming back to this, so where I was, this is the place where I was. So, so in principle, I can dominate over the Casimir-Polder potential, and I can measure the witness, as I said, and if the witness is positive, I can ascertain that gravity is quantum in nature. And if you don't like the basis-dependent witness, so here I've created a basis-dependent witness. But if you want basis-independent, in principle, you can compute it by looking at all possible correlation in the spin direction. It's sigma x, sigma y, sigma z. So it will be a I think all possible correlations. If you measure it, then you can construct von Neumann's entropy as well. And you can show that the von Neumann entropy would increase with time in this process if the gravity is quantum in nature. Of course, having said so, there are many problems. One of the problem is that the spins are embedded in your diamond, so you have to make sure that the diamond itself is extremely pure. If there is a small amount of impurity, the nuclear spin will interact with your electronic spin and can decoher the system. So I need to cool my internal degrees of freedom of my diamond, and I have to cool it to the extent that there is no phonon vibration at all. So for that, I need a cooling something like millikelvin temperature to cool the inside of the diamond. I have to cool it from outside as well, because if even the best of the best vacuum, there are air molecules, they will scatter and they will decoher my system. So I have to cool the entire setup to around millikelvin temperatures to avoid any kind of decoherence effects. Even a photon absorption and emission can destroy my coherence of my system. So I have to take into account of all these kind of small effects to get rid of the problem. Now we are dealing with the spins, so essentially it will create a dipole effect. But the dipole effect goes as 1 over r to the power cube, 1 over r to the power 3. So, and we are looking at 1 over r potential. So the dipole effect is not the biggest problem for us. As I said, the biggest problem remains the Casimir effect. And in order to create this macroscopic superposition, which we are talking about, something like micrometer, hundreds of micrometer, I need a huge magnetic field gradient, roughly 10 raised to 6 Tesla per meter. And I have to apply that roughly around 500, the acceleration time, the acceleration is roughly 500 meter per second square. So a huge amount of acceleration I need to give to create this macroscopic superposition. So all these numbers which we are demanding here are not available in any laboratory on Earth. So we can try to minimize these numbers in the sense that make it something which is reasonable so that we can perform the experiment, duly perform the experiment in future. Or if we want to live with this experiment, then these numbers, then we really have to really work hard with the technology now. So some of the things which I have discussed already. So as I said, that I need to put the system in a very low temperature. So the pressure of the vacuum has to be below even 10 raised to minus 15 Pascal. And you would in the next experiment, next design, I would show that there are certain things which you can overcome. And one of the things which you can overcome is this Casimir-Polder potential. And this you can overcome by creating a Faraday cage. So what happens is that, as I said, that the Casimir-Polder potential goes as the distance to the power 7, where capital R is the radius of my macroscopic objects and epsilon is your dielectric constant. So you know for two spherical system how the Casimir-Polder potential behaves. But if I can mitigate that problem by by putting a plate which is roughly a millimeter size plate, and it is a conducting plate with a thickness of a micrometer. It could be a even copper plate. I can insert a copper plate and try to mitigate this problem. So what will happen here in the system 1 and system 2 will not see this Casimir-Polder potential, but then the system 1 will feel the Casimir-Polder potential because of the screen. So that will exert a Casimir-Polder. Now, one has to make sure that the screen is classical. If the fluctuations of the screen becomes such that it becomes quantum away from its ground state, then in principle you can entangle them as well. So you have to make sure that the screen does not gets entangled with my system 1 and system 2. So I have to make sure that the stiffness of the screen should be high enough such that it doesn't vibrate at all. So there should not be any dynamical degrees of freedom. It should be very, very static. So these are some of the things which we are now, very recently, we are now computing essentially to conceptualize this kind of experiment in near future. And as you said, as you see that there are all these nitty-gritty details comes in to compute this kind of, to perform this kind of experiment. And just to give you some number, maybe this is the plot which may be interesting to see, that we are able to now reduce this inhomogeneous magnetic field. You don't require 10⁶ Tesla per meter. You can bring it down to 10⁴ Tesla per meter, which is actually, the experimentalists can use these numbers in their laboratory by inserting a sheet of roughly the width, which is roughly given by micrometer. And these are the density of your diamond, essentially. And you see on your y-axis, there is an effective phase. And in the x-axis, there is the mass of the system. So we are able to bring roughly 1 order of magnitude smaller masses. Keep in mind, the best record is held by the Vienna group, by Zeilinger's group, which has created the macroscopic superposition of 10⁻23 kilograms. And now we are talking about 8 orders of magnitude of jump in creating the macroscopic superposition. So right now, people are trying to create macroscopic superposition, which roughly 1 part in 10⁻20 kilograms. So there are colleagues of ours, and we are involved in the experiment in Israel. They're trying to create a 10⁻20 kilogram objects in a macroscopic superposition. But even from 10⁻20 to 10⁻15 is a huge jump, 5 orders of magnitude, and it's a big, big challenge for any laboratory. And the cost we are going to pay is the effective phase is now going to be roughly 0.01 of that range. So it means that in order to get the real phase of order 1, I need to perform this experiment roughly 1 over square root of n. So 0.01 means I have to repeat the experiment roughly 10⁴ times. And if each experiment takes roughly 1 second, I have to run the experiment for 10⁴ times seconds, that many seconds. So all these small problems are, they creep in. You try to solve one problem in experiment physics, then immediately you are bitten by the other problem. So that's the kind of lesson we have learned. In the process, we have also learned that even diamond cannot be a good choice, because, as I said, the diamond has impurities, but diamond has some dielectric, it has its own, not only dielectric constant, but it has a susceptibility, magnetic susceptibility. If a diamond is kept in a Stern-Gerlach, then what diamond will do is that there will be induced diamagnetism on my diamond, and that also causes trouble. Because of that, the motion of the diamond starts zittering. So it's very hard to control the geodesics of the diamond in this process. So maybe we have to invent a completely new material, or maybe coat the diamond with nickel kind of like coating, which actually being used also by Google for their quantum computing processes. So you have to even engineer the material science as well. As I was telling you about the witness, that the witness which we constructed were not the optimistic witness, not the most ideal witness. Recently, some of our collaborators have created the most efficient witness, and this witness is given by the unit matrix I squared, identity matrix I squared minus sigma x, sigma y, z, the Pauli matrices. And if the witness is negative, then we can, with respect to the density matrix, then we can say that, it turns out that this is much better witness than the one which we had proposed way back in 2017. So this plot actually tells us, as I was discussing a little bit about the collisional decoherence, that I'm allowing the system to free fall, but I have a chamber, I have a certain pressure, I have a certain temperature. So this ambience temperature, the ambience pressure, everything will matter. Even how many air molecules are there in my vacuum, even that will matter, because that will lead to destroy the coherence time scale of my system. So what it tells us that I have to be, my decoherence, on my y-axis I have the decoherence rate, on my x-axis is the number density of my air molecule, and if I want to have the witness, if I want to see that witness, I have to be above this dotted line. So there are all possible, all the small, nitty-gritty details comes in, and as you can see, as I reduce the temperature, I get a different kind of witness, different kind of decoherence rates and things like that. So and again, this one plot which tells you that how big the size of the plate should be. Because if the plate is too big, then again, it's not as feasible. If I want to do the experiment, the plate has to be sufficiently, there should be some minimal length of the plate such that for a given density of the plate, it does not vibrate, it does not entangle with system 1 and system 2. It behaves still like a classical system. So all these effects comes into the game to put constraint on even the nature of the plate. We are inserting in between system 1 and system 2. So just to give you, because my time is running out, so in 5 minutes, just to highlight some theoretical aspects as well. So you see that this one protocol is a very simple protocol, but it unites many, many different areas of physics. I have given you some glimpse of it. You have to change your material way of thinking about the material science. You have to come up perhaps with a completely new material. I have to find out decoherence witness. I have to find out what's the right witness. I'm dealing with the Casimir patch potential. In the process, I can even measure Casimir potential. If I cannot do this experiment, I can measure a very close range Casimir potential with different geometries. As I said, there's a condensed matter problem comes in because I need whatever the object is has to be very, very pure. Because keep in mind that in presence of external magnetic field, the nuclear spins will affect your electronic spin. Of course, the gyromagnetic ratio is different. Roughly, the difference is 1,000 times. So if there are 1,000, if there are more impurities, there are more nucleus which will have spins not aligned but randomly distributed, and they will cause decoherence for my electronic spin. So there are many small problems, and then not only that, I have not discussed how to release the system. For that itself, I require atom optics, trapping, and levitation techniques. And let me briefly explain that this protocol now, even CERN has shown some interest, because you see the CERN, the ALICE experiment in CERN creates very heavy charged particle. Now you can ask the question that can you do the same experiment? Of course, gravity is 1 billion times harder, but the charged particle, because of the electromagnetic strength is so strong, you can do perhaps similar experiment with the charged particle and show that the photon is quantum. Of course, in the case of photon, we know it's quantum. That's a trivial thing. But now what you can do is that you can probe physics beyond the standard model. If the photon, if the electromagnetic photon, the standard model photon, if it interacts with a hidden photon, then of course it will change it will bring in one loop effect, and maybe you are sensitive to that one loop effect. It will change your entanglement phase. And if you know your Maxwell's background, which we know very well because it's QED, we know the QED very well. We know the entanglement phase due to purely from the QED effect. Then anything beyond QED, you can capture it through this experiment. So you see that even physics beyond the standard model, you can test it this kind of experiment. You can have an axion or a hidden extra photon, U1s. These are things which you can learn. So another one thing which I did not discuss, that in order to do the experiment, one thing is that you need to have a very precise magnetic field. And the question is, how do you obtain a very precise magnetic field? So the way you have to think about is that you have to have a very precise number of the electrons passing through the current. And it should be so precise that it has to be the current has to be treated in a quantum mechanical sense. So I should be able to know exactly how many electrons are passing, the flux I need to know exactly. So I need to put this this number density in a coherent state, keep sacrificing my phase of my current. So my current has to be quantized. I need to develop some kind of superconducting current in some sense. Even this technology is not existing. So en route to doing this experiment, I need to do many small experiments. Each one of those are actually path breaking in the sense they are bringing a new technology altogether. But hopefully that maybe given 20-25 years time from now, maybe this kind of experiment will be possible to do what LIGO has taken. You see, the LIGO started way back in the 80s, and it took 20, 30 years, 40 years to do this kind of experiment. So in the same vein, if we start from now, maybe 25, 30 years from now, with the change in the technology, we will be able to perform this kind of sensitive experiment. So coming back in 2 minutes time, maybe or 1 minute, there is of course a very interesting formal theoretical aspects comes into the game. That what it tells us that if the two quantum systems are entangled because of purely gravity, quantum nature of gravity, then essentially we are all entangled. And possibly we can test it in even in not only in experiment, but also we can test it in our theoretical calculations. So this is something very trivial. I mean, I will not go into that. You know it very well. Any quantum system, the entropy is only entanglement entropy, because the whole system's entropy is the pure state, is the entropy is 0. So the entanglement entropy is the critical ingredient, which tells us that because of gravity, there's a universal entanglement between all of us. And the question is, how can you compute this universal entanglement? So you can perform, this is just simple calculation, which we have done it for our setup. But now you can say that, hey, look, if I modify the nature of gravity, if I modify the graviton propagator, how the entanglement phase will be different. Or you can ask the question, suppose if I take two macroscopic masses, just to give an example, I can try to scratch even the hair of because of a black hole. Suppose if black hole is not purely a classical system, suppose if it's a quantum system, then can I entangle these two systems? And you can ask these kind of questions even at the level of probing the infrared aspects of quantum gravity. And what you can show is that, or what we have shown here, that if you have a system A and system B, they are interacting gravitationally, and system A has n number of particles and system B has n number of particles in in 2 dimensions, 3 dimensions, and higher dimensions. What you can show is that the entanglement growth of the entanglement rate, the growth of entanglement rate has a universal behavior, which is a kind of like a logarithmic growth in very slow growth in the entanglement entropy. And so these are the two plots which are down below, shows that how the two systems, which are self-gravitating systems, how they are entangling with each other depending on how many states they have. So n equals to 10, 25, 50, 75, 100. You see that there is a universality in the growth of these entanglement. And in the upper half, I have got two plots which actually tells you that how if you change the behavior of the GR, essentially if you have higher order corrections maybe, depending on that, you can even study how the entanglement phase builds up. So for Newton's gravity, actually, you will see the entanglement phase keeps increasing as we go shorter and shorter distances. But that may not be the case for different other kinds of gravity. So you can actually probe the nature of quantum entanglement, and irrespective of your area CFT, now you can talk about quantum gravity, even in the infrared, how it affects your infrared aspects of your gravity. So because I'm really running out of time, so I have taken 2 more extra minutes. So I apologize for that. So let me conclude. So I believe that this is, testing quantum nature of gravity is the final frontier. It's the one protocol actually you can use it for even testing not only gravity, but you can also use it to probe physics beyond the standard model. So you see that, but it requires huge amount of experimental effort. This is the problem for our future generation. Maybe this kind of experiments can be done, can be performed, and of course, if it can be done, it would be an excellent opportunity for all of us. So with this, let me thank all of you for your kind attention, and I'm happy to, take your time.
So, Anupam, I did ask a few questions. Can I be permitted to ask a couple more? Well, the first one is, I want to congratulate you for a very nice presentation. This is an experimental quantum theory project, and you've done a very good job with the experimental details. So if I understand you correctly, you have spin states, which under magnetic fields show the lab type of situation, and then it's graviton exchange which entangles these states. Am I right? And the graviton exchange, as you correctly point out, has to be off-shell. So, the question arises, of course, gravity, as you correctly say, is a weakness to this entanglement process. But can you test the property of the weakness? For instance, being off-shell, it will have a tiny bit of longitudinal polarization, which an on-shell graviton will not have. So is it possible to sort of bring out that, or maybe a mass, the graviton has a bit of mass because it's off-shell. So there are these issues which could be an addendum to your experiment where you can say something about the witness. So that was the first comment. Well, I have one more question, and that is that because you need just two-level systems for this entanglement, can I not also imagine a situation with photons, photon helicity states, and they're entangled through gravity? I don't know how probably an impossible experiment. I'm not an experimentalist, but this just brings to mind because two-level systems have a certain commonality. So whether photon polarization states or helicity states could be used to repeat it, to have a kind of experiment. Because this coupling of photons is better than a coupling of spins to gravity. I mean, that's very clear. And there will be some bending, some lensing, which you know all about. So I think there will be there will be no material problems because it's photons and vacuum. So I was wondering whether it would be a cleaner test. And just a short comment, you're so right about entanglement entropy, because when we did the calculation of black hole entropy in quantum gravity in the years ago, Mishko and I, the calculation was indeed an entanglement entropy calculation, straightforwardly, and then you just use the rules of quantum gravity go to the extent, and you find that the Bekenstein-Hawking area must have an infinite series of corrections. So that's the thing. I mean, you're absolutely right. It was wonderful talk. Thank you very much.
Very beautiful questions. I think these are all these very relevant questions. So, in principle, okay. So even, I mean, to be honest, that if I believe in quantum nature of gravity, even LIGO experiment, which is detecting these gravitons, these are actually virtual gravitons because of all this black hole, but black hole coalescing black hole. But the distance is so far that these the virtuality almost vanishes and behaves almost like an on-shell system. Now, in principle, even in LIGO, you can ask the question, can I really, from the polarization, can I really see some effect? And in principle, it is possible, but the problem is that the LIGO has very, very heavy mirrors. So what I need is that I need to create a quantum superposition of these mirrors. And if I can put the quantum superposition of the mirror, then I shall be able to see that how the mirrors are getting entangled because of the impinging gravitational waves, if the gravitons are coming like in a quanta, say for instance. So in principle, it is, I mean, these are very thoughtful and very beautiful ideas. One can do it. The only problem is that here we are paying the price of the mirrors are very, very heavy. So that's one of the difficulty. As I've kind of like tried to convince that even for 10⁻⁻15 kilogram masses, I need to jump 5 orders of magnitude right now, and that itself is very, very hard. But nevertheless, thinking about all these directions are very, very fruitful. In principle, people have also tried with the photons. I mean, they try to create a very, very strong laser beam, and then they try to see, because the photon interaction with the graviton and looking into the effect of polarization. So people have done this kind of theoretical calculations, but it turns out that the numbers which they get are very, very tiny. And that makes it slightly harder to measure these kind of phases. But having said so, all these are very interesting. Even I was asking this question to Abhay a couple of months ago, that I met Abhay and we were discussing about this protocol, and I asked him that could I really test some loop quantum gravity effect? Maybe there is some non-perturbative effect which one can look into this kind of through this experiment. And so far, I mean, Abhay was not very positive about it. That he said that, look, I mean, perhaps it will not be possible for loop quantum gravity effect to be seen at even at the micro distances, which is fairly correct, I mean, from his formulations. But nevertheless, one can, as I said, that we know very little about the nature of classical gravity at very small distances. And that makes it, suspense that, who knows what gravity comes up with at very, very short distances. So I think, all these directions are very, very important to think about. And we should all think about it, yeah.
So,
can I ask the question?
Yeah.
Yes. It was very interesting to see and to hear your lecture about such interesting physical theory. And I would like to ask you about the causality principle. Hear me?
I'm sorry.
Causality principle. What's about the principle of causality?
That's a very good question, actually. So in principle, in experiment, if you can think about that, suppose your system 1 and system 2 are slightly outside your light cone to begin with, but when you drop it, you are inside the light cone. Then even you can test the causality also. So yes, it's a very beautiful way of thinking. So suppose I create my two superposition where they are not overlapping in the light cone, but I let it free fall, and after say some time tau, if they are inside the light cone, then essentially they will entangle. So you would see how the entanglement phase is developing through this kind of controlled experiment to test the very essence of the light cone structure itself. So in principle, if you are very adventurous, you can do this kind of experiment. And of course, I think nobody has tested this kind of at very small distances, how even our light cone structure behaves. So I think it's a wonderful thoughts.
Anupam, can you hear me?
Yeah. Oh, hi, Sudhakar.
Hi. Yeah. Okay. Congratulations for nice talk and nice presentation. But something which still worries me is that the examples you start with photon diagrams, scattering diagram, and take those analogy towards gravity, there is one issue. Unlike all other interactions which are mainly carried by some electrical charge, particle charge, but we know gravity is something different. It is basically interaction between energy and energy, right? So it's actually like an omnipotent way. So these analogies carrying out and doing the experiment, namely bringing out the quantum nature of gravity between two isolated systems. How do I create a gravitationally two isolated system? That issue still bothers me. It is always there is some interaction between them. It is very difficult for me to isolate two systems and probe into the quantum nature of gravity, because they are always there, because it is an interaction between energy and energy. So the experimental setup to probe the gravity itself, when gravity itself is there, is still that is a dilemma discussions to me.
No, it's a very, very good question. Very good question. So the question which Sudhakar is asking that, so we are looking into the quantum aspects here, but there is of course a huge Earth's gravitational potential, or even the Moon's gravitational potential. How do you get rid of this? So essentially, in order to do this experiment, we have to really. That's why I kind of like I was very interested in the Indian community right now because of ISRO's collaboration, because you really have to go into the space in a freely falling system. Even then you cannot get rid of it because there's a gravity gradient noise. The Riemann term is there, and depending on the size of your laboratory, and the Riemann term will give you some contribution, classical phase. So you have to know all the classical phase very, very accurately in order to perform this kind of experiments even in space. So there are two possibilities. First of all, we have to do it in a free fall. Either we dig very deep under the ground and let it fall the system, or I take it into the space and do the experiment. And I believe that this is the place where I think if we can convince our organization like ISRO, it's a win-win case, because first of all, it's like a technological demonstration that I can do this kind of experiment in space, and secondly, I can minimize all the classical gravity noise going into the space, like exactly similar kind of problems also faced by LISA or LISA Pathfinder. So no, these are absolutely wonderful questions, and you have to think about this gravity gradient noise. And hopefully this week we'll come up with some of these calculations. Even Kip Thorne had a very interesting paper. He wrote it a long time ago, that he was imagining doing this kind of experiment in space with the LISA, gravitational waves. So if an astronaut passes by the setup, he will induce some gravitational waves.
Yes.
So how do you get rid of that? So all these questions which you are asking, they are wonderful questions, and you have to take all of them into account. You have to know your background so precise that you can measure this entanglement phase.
There is one more issue, is that all this field theory or quantum theory, gravity, whatever we are doing, we have assumed that as if we are in an equilibrium system. Whereas our real world is, we live in an expanding universe. It is never in equilibrium. So that non-equilibrium effects we have to take into account. So for such precise measurements we are talking, even the non-equilibrium parts needs to be included for any prediction.
That's true, but you see that again, these effects, so the laboratory size is very, very tiny. So the real experiment is done roughly take millimeter size. And all these effects which we are talking about, all the external effects, these are millimeter divided by the size, the distance away from you are. So if you take the quantum effects due to the entire cosmos, so these effects are extremely very, very tiny at those scales. So like if the primordial gravitational waves passes by, again it's the frequency. At what frequency they are passing by and what frequency I'm doing this experiment. So of course these are the systematics. In principle you can isolate it, but what happens is, suppose there's a meteorite passes by my experiment, then you have to be careful. You have to maybe, so one idea is that you take your system, you rotate the system every time. Every run you rotate the system to get rid of these systematics. So even in LISA, people use some of these techniques with LISA Pathfinder, that they rotate their entire laboratory to get rid of all the classical systematics. So one of the things is all these systematics will not entangle the system. They act like your noise, definitely.
That's right. So the only thing wanted to see that what we are probing and how are they comparable to these external.
Absolutely.
noise.
Absolutely. So yeah, I agree with you.
That needs to be settled down before we really do an experiment.
Yeah, absolutely. So you have to know your background precisely so that you can overcome. So in this respect, this will be perhaps if we can do this experiment, it will be the most delicate experiments ever one can ever imagine. So by no means I'm saying that this experiment will be easy. It's extremely, extremely challenging. But if one can do it, it is worth doing it.
No, that's right. Yes, I agree. Thank you. So our things are running in.
Oh, we are at home. You see that I'm giving a talk from home.
I know.
Our university is closed. We can't go to the university.
Yeah, good.
And life is a bit normal. In the north, we haven't had enough casualties. But we know many people who have lost their parents, but they cannot even see their parents. So yeah, unfortunate thing has happened, of course.
Okay, give my regards to Eric and others.
Of course, I will definitely do that. Yeah.
Okay, thank you very much.
Thanks a lot. Yeah.
So, hi, Professor Mazumdar. So, thanks a lot for your very interesting talk. Unfortunately, Shumanto actually just wrote to me that he had to leave for some emergencies. He's not sure actually if he'll make it back in time to till the end of the question session. So he just told me to convey this and thanks a lot for the very interesting talk. And if there are further questions, please just unmute yourself and go ahead with the questions. So I guess there are no further questions. Okay, so let's all thank the speaker and hope to hear from you soon again about this very interesting idea. So thanks a lot.
Thanks. Thank you very much. Thanks a lot. Yeah.